Hey guys, welcome back. This is lecture 4, so this is the titration lecture. This is actually scheduled to be given, I think, on Friday. Yeah, Friday. So I will go ahead and get started with this. The first thing we are going to do, as always, is a review of what we have talked about previously. So I'm going to share my little piece of paper here. I've decided to do this rather than just on blank paper, to do it on the slides as I would do it in class. So hopefully this will help. You will get a marked up copy if you want one. So if you want a marked up copy like this of all the stuff that I'm writing down, let me know. Send me an email. I can email this to you. It is not a big deal, not at all. Okay, so just let me know and I'll take care of it. So it says nitrous acid, HNO2, has a Ka of 4.5 times 10 to the minus 4th. What's the H plus, OH minus, pH, and POH of this solution? Well, I know that nitrous acid is HNO2. This is an acid dissociation, Ka, so I'm going to get an H plus and an NO2 minus. That's what's going to happen when I do that. My Ka, which has a value of 4.5 times 10 to the minus 4th, is going to be equal to the concentration of H plus times the concentration of NO2 minus over the concentration of HNO2. Okay, so that's the structure of my Ka. When we get into what we're looking for, I seem to have left something out of this question, because in order for me, well, no. Let me think. I'm thinking. So this is my R. I don't have any initial conditions, but I know that this is going to be a minus x, this is going to be a plus x, this is going to be a plus x, and that means that as this is written, I have a minus x, and a plus x, and that's not going to be enough for me to be able to solve this. So that was what I identified, was I don't have an initial concentration. But if I give you an initial concentration, and I'm just going to say 0.1 molar, because why not? It's easy. It's, fairly easy for us to work with. Then I can put that here. We assume that both of those are 0 when we start this, because we're breaking down that HNO2. So all I know is how much HNO2 I put into this. That's that 0.1. And then technically, this is going to be 0.1 minus x, but we assume that the x is small, and so we don't include it. You'll see that I cross it out every time. For me, that's a reminder that I should be including it, that technically that calculation should have it, but I'm going to ignore it this time, and that's my way of specifying that I have ignored it so that I can go ahead and do this calculation. Now, I have done this calculation for many classes with not making the assumption, and that's why I have to do it this way in my own head, because otherwise I don't know if I made the assumption or not. So that's all that is that I'm crossing it out, so I know that I've made the assumption. So if Ka is 4.5 times 10 to the minus 4th, and that's equal to the H plus, which we have as x, and the NO2 minus, which we also have as x, over the concentration of the HNO2, which is 0.1, because we're ignoring that x, that means we're going to have x squared equal to 4.5 times 10 to the minus 4th times 0.1. And of course, finding my calculator, I can do some happy math. And 4.5 times 10 to the minus 4th times 0.1, my x squared is equal to 4.5 times 10 to the minus 5th, because that's what happens when you multiply those together. And that means my x is the square root of that, which has a value of, second answer, 0.0067. Okay, so that's my concentration that I would put in here. That's what x is equal to. And of course, if I wanted to calculate the equilibrium concentration of the HNO2, I'd take the 0.1, I'd subtract the number that I just calculated, and that would give me a 0.0933. So it's not very different, and that's what we're talking about. And if we do a calculation and we say, okay, that x, 0.0067 divided by 0.1 times 100 gives me 6.7%. So technically, it's not within the realm that we should be accepting, but that is okay. For this, we're going to go with it, okay? So if that's my H plus, is that 0.000067, and that's my H plus, so that's equal to the H plus concentration. If I want my pH, that's equal to the negative log of the 0.0067. So I can take the negative log of what I just calculated. And that gives me negative 0.821. And I know people sometimes freak out because we get a negative number there, but it is totally possible to have a very large H plus concentration and get a negative pH. We try not to talk about it so often because it seems weird, but that is perfectly acceptable. If I want pOH, that's equal to 14 minus the pH, so minus the 0.821, and that means we have 14 minus that answer that I just calculated, and that gives me 14.83. That's my pOH. So I have pH, pOH, H plus, because that's right here, and then my OH minus is going to equal 10 to the negative pOH 14.83, which is going to be second 10x, negative, second 10x, negative, second answer, and that gives me 1.5 times 10 to the negative 15th. Okay, so that's how I would calculate all the concentrations that go with that. Now, again, I didn't give you an initial concentration, so that calculation in and of itself cannot be done. You need a concentration to work with that. And if you see something like this on test, say, without an initial concentration, I can't do this, but I assume the initial concentration is pick something and then do the math. Okay, just like what I just did. I picked something and I did the math. Okay, so in the event that that happens on a test, that's what you need to do. Okay, so there's that one. Let's see what our next one is. So, aniline, C6H5NH2, has a Kb of 3.8 times 10 to the minus 10th. What's the H plus, OH minus, pH, pOH, C6H5NH3 plus, and C6H5NH2 at equilibrium? First thing I'm going to do is write C6H5NH2. I know that that is a base, so I'm going to react that with water. And I know it's a base because of the presence of the N and NH groups. So that NH typically indicates that it's a base, Lewis base specifically, so we can pick up another proton with the lone pair of electrons on the nitrogen. So it's going to do exactly that. So we're going to end up with C6H5NH3 plus, which I know because that's what it's written right there. So that is what I'm going to get, plus the OH minus that's going to be left over when we do that. Now, H2O is a liquid, so we don't care about that at all. It's only present to balance my equation, all right? My initial concentrations will go here, my change, and my equilibrium. But again, I don't have an initial concentration, so I have the exact same problem that I had before. So let's go with what we started with last time. So we'll start with 0.1 here. We're going to get a Go back. We're going to get a negative x. For every one of those that reacts with the water, we're going to end up with one of these and one of these, okay? And so at equilibrium, this is going to be 0.1 minus x. We're going to ignore the x. And then this is going to be x, and this is going to be x. So those are the values that we're looking for there. Now, I know that the Kb is going to be equal to OH minus times that C6H5, and it's not going to fit, so I'm not going to bother. I'm going to move it because it won't fit there. So my Kb is equal to C6H5NH3 plus times the OH minus divided by the concentration of C6H5 H5, and H2. Okay, I know that that has a value of 3.8 times 10 to the minus 10th. And I also know that this times 10 to the minus 10th is equal to x times x over 0.1. So we end up with an x squared being equal to 3.8 times 10 to the minus 10th times 0.1, which should be 3.8 times 10 to the negative 11. And it is. I can't do most of that in my head, but that one I usually remember after I've done it once. So if I take the square root of both sides, second square root second answer, I end up with 6.16 times 10 to the minus 6. Okay, so that's the concentration that goes right here, 6.16 times 10 to the minus 6. And of course, that's going to be for this one as well. And so if we wanted to calculate the actual concentration of the base at equilibrium, we take our 0.1, we subtract that number, and we end up with 0.09999 out there. I'm going to cut it off at one sig fig. And of course, it doesn't matter how many I keep, because once I get to the thing after the 3, that rounds up to 0.1. Okay, so since it rounds back to 0.1, we're going to use 0.1. Okay. So that's what we have there. That gives us the concentration for our H plus. Ooh, and it's not H plus, it's the OH minus. That's right, it's base. So the OH minus is equal to 6.16 times 10 to the minus 6. That means that our H plus is going to be equal to 1 times 10 to the minus 14th divided by 6.16 times 10 to the minus 6. And that's one of the ways that we can calculate it. So 1 times 10 to the minus 14th divided by 6.16 to the negative 6th. And that gives me 6.06 times 10 to the minus 20th. Okay. Oh, I did it wrong. Sorry, my math is wrong. I didn't divide, I multiplied. That's much better. I looked at that number and said, that's really, really tiny. I don't know that that feels comfortable to me. And it's not, and it's because I did the math wrong. So rather than doing a division in my calculator, I had done a multiplication. So 1.65 times 10 to the minus 9th. Okay. pH is going to be the negative log of that number. And that gives me 8.78. And my pOH is the negative log of that 6.16 times 10 to the minus 6, which gives me 5.21. And if I take 5.21 and I add that 8.78, I should get something approximating 14, which I do. With the rounding error, I get 13.99, which I would expect because we've rounded things, so we're going to have some small errors from that, okay? So those are the values that they asked me for there in terms of the H plus, the OH minus, the pH, the pOH. Now they want to know about the C6, H5, and H3 plus. That's 6.1 times 10 to the minus 6. Okay, so my C6, H5, and H3 plus is equal to 6.16 times 10 to the minus 6. And the concentration of C6, H5, and H2 is equal to that 0.099993. Okay. Now again, it really shouldn't have all of those decimal places, but we're going to keep those just to show that it is actually not 0.1. Okay. So the math is a little more pleasing when we have more figures. All right. So questions, comments, problems? I hope not. But if there are, you know how to reach me. Let's go ahead and do number 3. Aniline has a Kb of 3.8 times 10 to the minus 10th. The nitrous acid has a Ka of 4.5 times 10 to the minus 4th. What is the Ka of aniline and the Kb of nitrous acid? Okay, so the first thing I want to know, what's the Ka for aniline when the Kb is equal to 3.8 times 10 to the minus 10th. So my Ka is equal to Kw divided by Kb. So 1 times 10 to the minus 14th divided by that 3.8 times 10 to the minus 10th is going to give me the Ka for it. So 1 negative 14th divided by 3.8 negative 10. That gives me 2.63 times 10 to the minus 5th. Okay. When I do the math on the other one, so this is my aniline. I just want to label it. And when we talk about nitrous acid, Kb is going to be Kw divided by Ka, which is going to be 1 times 10 to the minus 14th divided by 4.5 times 10 to the minus 4th. 1 negative 14 divided by 4.5 to the negative 4th. That gives me 2.22 times 10 to the negative 11th. Okay. You can comment on if aniline is a better base or a better acid. Okay, so what I'm trying to compare here is which of those values is larger, the Ka or the Kb. The Kb is 10 to the minus 4th. The Ka is 10 to the minus 5th. So the Kb is bigger. Kb is bigger than Ka. That means it's a better base. When we talk about our nitrous acid, my Ka is 4.5 times 10 to the minus 4th. My Kb is 10 to the negative 11th. So since Ka is greater than Kb, it's a better acid. Okay. Now, is this a relevant question? Yeah, it is. And it's not always as obvious as the one that's been asked here. So sometimes we'll do this for things that we're not as familiar with that are actually, weaker acids or weaker bases. We may not know which one is the better species, okay? If they're both weak, we may not know which is the better. And so that's the kind of comparison that we're doing here, is to determine which is the better base or acid, okay? So there's 3. Let's talk about 4. Come on. Let's go. All right. pH of a 0.35 molar formic acid solution, HCOOH, is 2.11. What's Ka of the acid? Okay, it's formic acid, HCOOH. That acid dissociation gives me H plus HCOO. Too many C's. HCOO minus. This is my R. Then my initial, my change, and my equilibrium. My initial, this is 0.35. And I know that at equilibrium, the H plus is 10 to the negative 2.11, because it's 10 to the negative pH. So second 10x, and negative 2.11 gives me 0.00776. And I'm going to leave that like that for now. Now, understand, on my calculator, I'm keeping all of those numbers. So that's how we do that. Now, when we talk about our change, this is going to be a negative x. This is going to be a plus x. And this is going to be a plus x. That means that this HCOO minus is also the 0.00776. And my concentration of the acid is going to be 0.35 minus that answer. 35 minus the 0.0076. Okay. 0.35 minus that answer. That gives me 0.3422. My Ka has the structure H plus times HCOO minus over the concentration of HCOOH. I can plug in all of my equilibrium values. So that's 0.00776. I have 2 of those, so it's going to be squared. We're going to divide that by the number we just calculated, the 0.3422. All right. So I'm going to go back and do 10x to the negative 2.11 to get that whole number there. I'm going to square that. I'm going to divide that by the quantity, 0.35 minus the answer that we calculated, which is 0.0077624712. That's all my calculator will show me. And I end up with 1.76 times 10 to the minus 4. Okay. Now, is it really important that I keep all of the decimal places? No, but the more of them I keep, the more accurate that number is going to be comparative to what I would find in a table. Okay. So we want to maintain as much of the decimal places as we can while we're doing the calculations in our calculator. We want to truncate them only so that we can report them on our paperwork. So for the right number of sig figs. I tend to not fix for sig figs until the very end so that I can see that things were eventually truncated. Okay, so that's how I handle that. Questions, comments, problems on that one? Again, I hope not. So let's talk about 5. It says, what is the pH and pOH of a solution of 0.174 molar pyridine and a 0.177 molar pyridinium chloride? I hate that word, pyridinium chloride. If the Kb of pyridine equals 1.7 times 10 to the minus 9th, we want to know the pH and the pOH of this. We're given a concentration of pyridine, which is is that a 5 or is it 5? H5N equal to 0.174, and a concentration of this pyridinium chloride, C5H5NHCl, equals 0.177. So I see, when I look at this, what I see is that this is a base. This is its conjugate acid. That means that I can use pH is equal to pKa plus the log of the base over the acid. Okay. Now, I don't have a Ka at this point, but I can get one. I can take 1 times 10 to the minus 14th, divide that by 1.7 times 10 to the minus 9th, and I calculate Ka, Kw over Kb, as 5.88 times 10 to the minus 6. If I take the negative log of that, that gives me 5.22 or 5.23. I'm going to plug that in for pKa. I'm solving for pH, and I'm going to add the log of the base, concentration of the base is 0.174 over the concentration of the acid, 0.177. Now, can I always use this, Henderson-Hasselbalch equation? Even though we're talking about a base, yeah, I can. I just need to calculate the Ka for it. We make sure that everything is still set up the same way. Now, is there an equivalent pOH is equal to pKb plus the log of the acid over the base? Yes, but I don't want to have to remember 2 equations, so that's not what I'm going to do. And this is how I would plug all of that in. So I have my 5.23. I'm then going to add the log of 0.174 divided by 0.177. And I end up with 5.22 as my pH. My pOH is then 14 minus the 5.22, which is 8.77. And that was everything that they asked me for. Okay? So that's how I do that. Now, Henderson-Hasselbalch designed for acids, but can be used for bases. We just need to calculate a Ka to do so. All right, so make sure that you remember that when you're dealing with it. Can you do it the other way if you want to learn the equation? Yeah, absolutely. You can. I'm not going to do it. That's not how I'm going to handle it. Okay? Now, questions, comments, problems. Again, I hope not, but if you have any, please let me know. I'm going to go ahead and stop now that we've finished the review, and I'm going to stop this recording. I will get this uploaded, and I will come back and we will talk about what we're going to talk about in titrations. All right, see you soon.